The values of the amplitude and the phase are thought, as with all fields, are thought of as intrinsic properties of the points in the high-dimensional space with which they're associated. And so, for example, the fact that the integral over the entirety of the configuration space of the square of the amplitude of the universe's wave function is invariably equal to 1 is going to have to be thought of not as following analytically from the sorts of physical objects wave functions are, which it certainly can't, but as a physical law or maybe as an initial condition or something like that. What the wave function does and how it interacts with whatever other concrete fundamental physical objects there may happen to be and where it fits into the overall quantum mechanical picture of the world is going to depend on precisely how the measurement problem gets solved. On Bohmian mechanics, for example, the world is going to consist of exactly 2 physical objects. One of those is the universal wave function, and the other is the universal particle floating around in this high-dimensional space, what Shelley Goldstein calls the marvelous point. And the story of the world consists in its entirety of a continuous succession of changes of the shape of the former, that is the wave function, and a continuous succession of changes in the position of the latter, the marvelous point. And the dynamical laws that govern all these changes, that is the Schrodinger equation and the Bohmian guidance condition, are completely deterministic, and in the high-dimensional space in which these objects live, completely local as well. On the GRW theory, or for that matter on any theory of the collapse, the world is going to consist, on this way of looking at it, of exactly 1 physical object, the universal wave function. What happens, all that happens, is that that function changes its shape in accord with the theory's dynamical laws. And those changes are not entirely continuous, and the laws which govern them are not entirely deterministic, and even in the high-dimensional space, not entirely local either. Anyway, the particularly urgent question is where, in this picture, all the tables and chairs and buildings and people are. The particularly urgent question is how it can possibly have come to pass, on a picture like this one, that there appear to us to be multiple particles moving around in a 3-dimensional space in the non-relativistic case. And the thing to keep in mind, or at least the way one is going to have to approach this if one wants to make sense out of this kind of a picture, is that at the end of the day, what it is to be a table or a chair or a building or a person is, like we were talking about with temperature before, is to occupy a certain location in the causal map of the world. The thing to keep in mind, to put it slightly differently, is that the production of geometrical appearances is, at the end of the day, a matter of dynamics. Think, to begin with, of a real concrete d-dimensional space with a single classical particle floating around in it under the influence of a classical Hamiltonian H. And suppose that there is some orthogonal coordinatization of this d-dimensional space, call that coordinatization C, on which H happens to take the form on top here. Okay? And what you're supposed to notice about that form is just that the potential depends on a number that has the form of that has the Pythagorean form of a 3-dimensional distance. Okay? Good. So suppose that there's some coordinatization where it takes this form, where I and j range over the integers from 1 to d over 3 inclusive. Good. Looked at in C then, the position coordinates of this particle are going to evolve in time exactly as if they were the coordinates of d over 3 classical particles floating around in a 3-dimensional space and interacting with one another in accord with a law which is built up out of the geometrical structures of that 3-dimensional space and which depends on the interparticle distance in that 3-dimensional space and which is invariant under the symmetries of that 3-dimensional space and which has and which, if you rewrite it in terms of x, y, z, has this familiar mathematical form on the bottom. Good. This is so. Here I'm in a d-dimensional space. Okay, that is It's some high-dimensional space. I notice that the Hamiltonian, that there's some coordinate system, there's some orthogonal coordinatization of this space where the Hamiltonian takes this form. Okay? If that's the case, then the motions of the evolutions of these coordinates in time, okay, are going to break down into triplets, okay, and are going to evolve like exactly like the XYZ coordinates of d over 3 particles in a three-dimensional space, moving under the influence of a three-dimensional Hamiltonian like this.
How many particles are you talking about?
I'm talking about so in the literal metaphysical picture, we're talking about one particle floating around in a 3n dimensional space. And we're talking about the possibility that this one particle, as it were, formally instantiates or enacts or something like that the coordinate evolutions associated with with n particles in a three-dimensional space. Yeah.
Was written in terms of configuration space coordinates and momenta. If you write it like that, you don't even see anything like a symplectic structure.
Yeah. No, I'm not. None of that is going to be important. Of course, you're right. None of that is going to be important to what I want to say here. I mean, let me go on a paragraph or two, and it'll be clear.
If there's one particle, what is it interacting with?
It's not interacting with anything. It's obeying this Hamiltonian. What? There's this Hamiltonian should be thought of as the energy associated with the particle being located at a particular point in the high-dimensional space. The high-dimensional space isn't translation invariant, anything like that. The particle being at certain points in the high-dimensional space is associated with different energies than the particle being at certain other points in the high-dimensional space. In conventional language, think of it as an equation of as a Hamiltonian for a particle moving around, say, in an externally imposed field of some kind. Okay? Okay. Good. This particle in this space, moving around under the influence of the Hamiltonian, this one, the first one, formally enacts, you might say, a system of d over 3 classical three-dimensional particles, the ith of which is the projection of the world particle onto the 3i minus 2, 3i minus 1, 3i subspace of the d-dimensional space in which the particle floats. And if we pretend, just for a moment, that the laws of ordinary three-dimensional Newtonian mechanics, together with the familiar three-dimensional Hamiltonian, the bottom one, in equation 2, can accommodate the existence of the tables and chairs and baseballs of our everyday experience of the world. Of course, a Hamiltonian like this in classical mechanics can't accommodate the existence of those kinds of systems. That's why we need quantum mechanics, okay? But just to illustrate the point quickly, pretend for a moment that they can, then we're going to be able to speak as well of formal enactments, not only of these individual particles, but of tables and chairs and baseballs, by which we mean the projections of the position of the world particle onto tensor products of various of the 3i minus 2, 3i minus 1, 3i, three-dimensional subspaces of the d-dimensional space in which the world particle floats. And these formally enacted tables and chairs and baseballs are clearly going to have precisely the same causal relations to one another and to their constituent formally enacted particles as genuine tables and chairs and baseballs and their constituent particles actually do. And so, insofar, and of course this is a big insofar, which will no doubt be much debated here, insofar as we have anything in the neighborhood of a functionalist understanding of what it is to be a table or a chair or a baseball, insofar, that is, as what it is to be a table or a chair or a baseball can be captured in terms of the causal relations of these objects to one another and to their constituent particles and so on, then These formally enacted tables and chairs and baseballs and particles must really be tables and chairs and baseballs and particles. And insofar as what it is to be a sentient observer can be captured in terms like these, then projections of the world particle onto those particular tensor products of three-dimensional subspaces of the d-dimensional space which correspond to such observers are necessarily going to have psychological experience. And it's plainly going to appear to such observers that the world is three-dimensional. Of course, insofar as we confine our considerations to the case of classical mechanics, all of this is a fairly idle academic entertainment. Because in the classical case, there's no reason to take these high-dimensional pictures seriously, because in the classical case, there is always already an option of saving the three-dimensional appearances by means of an exact and universal and fundamental theory of a thoroughly three-dimensional world. But the point of all this, of course, is that in the quantum mechanical case, we're dealing with something different. The point of all this is that in the quantum mechanical case, the reasons for taking these high-dimensional pictures seriously are, at least on the face of it, fairly powerful, given the kinds of demands for what it is to have a clear fundamental physical theory that I started out with. And the classical entertainment we've just been through has in it the crude beginnings of an account, or rather a set of accounts, of how it happens that there can be tables and chairs and baseballs and people and three-dimensional appearances in Bohm's theory and in the GRW theory and in any workable solution to the measurement problem in which high-dimensional quantum mechanical wave functions play an essential and inimitable and fundamental and sort of concrete role. The business of actually filling in the details of these accounts is not an altogether trivial matter and needs to be approached separately and anew for each particular way of solving the measurement problem, and requires that we attend carefully to exactly how it is that the things we call particles actually manifest themselves in our empirical experience of the world. In the Bohmian case, for example, there's patently not going to be any coordinate system of the high-dimensional space in which the coordinates of the world particle evolve in time exactly as if they were the coordinates of d/3 classical particles floating around in a three-dimensional space. And of course, we wouldn't want there to be a coordinate system like that, since the world we're looking to enact in this case isn't a classical one, but a quantum mechanical one. But what it is to enact a system of quantum mechanical particles is, on the other hand, not on the face of it so easy to say. The exact trajectories of quantum mechanical particles, if indeed quantum mechanical particles have any exact trajectories, as they do in Bohm's theory, certainly don't count among those features of the world to which we can ever have any direct empirical access. And so there can be no exact and particular claims about the motions of particles over and above what we have from the Schrödinger equation and the Born rule that we ought properly to be in the business of trying to underwrite in this case. And the situation in the GRW theory is apparently even worse. In that latter theory, after all, at least at the fundamental level, there's nothing particulate at all. But it turns out, and I won't drag you through this at the moment, but maybe there'll be more discussion of it as we go on. The short story is, it turns out that these challenges can be met, and these obstacles can be overcome, and that we're now able to write down clear and detailed and even what you might call elegant accounts of the emergence of the tables and chairs and pointers and three-dimensional space of our everyday experience of the world in theories like these. Accounts that avail themselves of no untoward philosophical shenanigans, accounts that appeal to nothing whatsoever above or apart or aside from what there is and what it does. And those accounts do indeed, at the end of the day, run very much along the lines of the classical entertainment that we went through above. Thanks.